So we're finally going to get to where we solve these differential equations using a power series. And we're going to start off with some really easy examples. So we're not going to start out with these ordinary types where we have to determine if it's ordinary or singular or anything like that. We're just going to have constant coefficients for our first example. So what we're going to do for each of the differentials is we're going to solve it using stuff that we learned earlier in the course. And then we're going to solve it using a series solution. And we're going to see if we can represent the series solution by maybe matching it up with maybe one of the Taylor or Maclaurin series, if at all possible. All right, so earlier in the course, we probably did this. So this is part A, dy dx, so we changed our y prime, is going to be equal to 2y. And then we can multiply both sides and divide both sides. So it's a separable differential. So dy over y is equal to 2 dx. And so we can write this as ln absolute y is going to be equal to 2x plus c. And then we can go through and raise both sides to the e power. So we can say absolute y is going to be equal to e to the 2x plus c. And then remember that trick where if you have e to the c, so it's e to the 2x, e to the c. And then we can write this as y equals technically plus or minus, I'll call it k, e to the 2x. All right? Or we could just ignore the plus or minus because now we have this as our initial value. So since we're in the positive realm, we're at the point 0, 1, then we don't necessarily need the positive negative going on there. So we can just get rid of this. And then to solve for k, we're just going to substitute 0 in for x, 1 in for y. So 1 is going to be equal to k e to the 2 times 0. That implies that k is equal to 1. And so our solution, y equals e to the 2x. All right, so that's going to be our initial value for this. Now, let's see how we're going to solve it using a series. All right, so it's a little bit tougher using a series. All right, so I'm going to write the original differential up here. So y prime minus 2y is going to be equal to 0. All right. So we're going to define y to be equal to the series n equals 0 to infinity c sub n x to the n. All right, so that's the first thing that we always do. If you write that on the test and I ask you to solve using a series, you at least get 1 point for that. Now the derivative of this, be careful. Y is going to be equal to series, we're going to say c sub n. The derivative of x is going to be n times x to the n minus 1. All right. Now we have to be really careful with the bounds because each time we take a derivative, what's going to happen is we are going to have to shift the index. All right. Now, why do we shift the index? Well, let's say n was 0. Well, that would mean we would get x to the minus 1 as a possible factor. And then if we divide, that means we have 1 over x. All right, so if for some reason we had x to the 0 minus 1, if n were equal to 0, which it can't be, then that would mean we'd have x to the minus 1 or 1 over x. And remember, we're trying to find at x sub naught equals 0. So in other words, that wouldn't be in the domain. In other words, it's not differentiable at that point. So we have to shift the index. All right, every time you take a derivative, you're going to shift the index. Now we're going to substitute back into the original differential equation. All right, so if we do that, by substitution, we are going to get series n equals 1 to infinity, c sub n, n, x to the n minus 1, minus 2 of the original y series. So that's n equals 0 to infinity, c sub n, x to the n, and that's going to be equal to 0. All right, so this is our y prime, and this is our minus 2y prime. All right. Now, our goal is to be able to somehow figure out the values of c sub n. All right, so the x is really going to be negligible to us. So if we could somehow get rid of all the x's, then we'd be in good shape. And what we're going to do every single time is if the indexes don't match, because ultimately what we'd like to do is we'd like to be able to factor the series out, because it's just a sum of terms and we can factor it. If we can do that, then we're in really good shape. All right, so one of our goals is to factor the series to get to just C sub n terms. All right, so that's one of the goals that we're always looking to do. And so in this case, what we're going to do is we're going to use a change of variable on both of the series. Okay, on the series. And essentially what we're going to do is we're going to change the index. All right, so how do we do that? All right, well, what we can do is we can say, for this series, right, let's use the relationship that n, or I'm sorry, let's say that n is going to be equal to k plus 1. And the reason I do that is because I want to factor out that x, if at all possible. All right, so we're focusing on just the x terms, and we're saying, okay, well, if we can do a change of index and somehow get the x's to be the same, then after that we might be able to worry about the indices. All right, so now n minus 1 is going to be equal to k, and that's going to be important because that means we're going to have to change the index of the bounds as well. This one we're not going to change, so we're going to say that n is equal to k for this one. All right, so now let's rewrite the series. All right, each of the series now in terms of k. So if we do that, now remember, n minus 1 is equal to k. So the lower bound is not going to be k equals 1, but now it's going to be k equals 0. All right, so we just substitute this 1 back into here. So n equals 1 minus 1 is 0. And then obviously infinity minus 1 is still infinity. Every time we see an n, we're going to replace that with a k plus 1. All right, so that's going to be c sub k plus 1 times k plus 1. All right, so notice that we're substituting for this n, and then x to the k plus 1 minus 1 is going to be x to the k. Minus 2 series, and this series we're just replacing n with k. So we get k equals 0 to infinity, c sub k x to the k, and that's going to be equal to 0. All right, so make sure that you're okay going through and doing this substitution. All right, if you have to go back and watch the video a few times to do this, make sure you do. All right, now I want you to notice that we can factor out a series of x to the k. All right, so we're going to factor out k equals 0. All right, and if we do that, so we're going to factor out the series k equals 0 to infinity of x to the k. And what's that going to leave us with? Well, that's going to leave us with c sub k plus 1 times k plus 1 minus 2 c sub k equals 0. All right, so where does that leave us? Well, it leaves us with two possible solutions. So right here, the only way that this could be equal to 0, right? Because remember, this whole equation has to be equal to 0. So what we're saying is this series has to be equal to 0, and the only way that's true is when x equals 0. And that's just the trivial solution. All right, so that doesn't really tell us much because, well, that's the point that we're trying to find. All right, so that doesn't really help us much at all with this. All right. However, what we also do is we set this equal to 0. C sub k plus 1 times k plus 1 minus 2c sub k equals 0. All right. And what we're going to do at this point is we are going to get a generating function. So we're going to figure out a recurrence relation. And we're going to solve this for the highest order of c. So in this case, it's going to be c sub k plus 1 that we're going to solve for. So we can say that c sub k plus 1 is going to be equal to, so I'm going to add 2c sub k to both sides, and I'm going to divide that by k plus 1. All right, and what this is a generating function, okay, or a recurrence relation. So I'm going to call it a generating function because it's going to generate our c sub n's. All right, most of the time we're going to refer to it as well as a recurrence relation. All right, and you might remember that from Calculus 2, or maybe you saw it in like discrete mathematics or something like that. If you've never seen it before, then we'll see it now. So I'm trying to spell it right. All right, so now we're on to our last step, being able to figure out what c sub k is. And what we're going to do is we're just going to insert 0, 1, 2, 3, 4, 5. So we're going to use this method of iteration. And method of iteration basically means we're just going to plug in numbers until we can guess a solution. Okay, you might have done that in Calculus 2. So here's what we're going to do. We're going to have values of k, and then we're going to evaluate our c sub k plus 1 is equal to 2c sub k, k plus 1. All right, and we're going to keep doing this until we can figure out what's really going on with this. Okay, so when k is equal to 0, that means we just get c sub 1 is going to be equal to 2c sub k, or c sub naught, excuse me. All right, and all I did was I just plugged in 0, 0, and 0. Right? For when k equals 1. C sub 2, so now I'm just plugging in 1, is going to be equal to 2c1 divided by 2. Okay? But remember, c1 is really 2c0, so we're just going to plug that back in, and this just becomes 2 times 2 times c0 over 2. All right, so let's hold on to that. And I know we can simplify that down into 2c0, okay? Let's just hold on to that for now again. All right? Now, let's plug in 2. C sub 3 is going to be equal to 2c2 divided by 3, which is going to be equal to 2. And again, all we're doing is we're substituting this back in for C2. So that's why we call it a recurrence relation. We're just building off of the previous iteration. So 2 times 2 times 2 times C0 divided by, so we have this 2 in the denominator, so we have 3 times 2. And now you can kind of see what's going on with this. We're just going to do a few more iterations of this, and then we'll be done. So let's just do 2 more just so we can be certain as to what's going on with this. All right, so when k is 3, and we can pretty much guess what's going to happen with this, C4 is going to be equal to 2C3 divided by 3 plus 1, which is 4. And all we're going to do is we're going to take the previous iteration, we're going to substitute it back in into C3. And when we do that, we get 2 times 2 times 2 times 2 C0 divided by 4 times 3 times 2. And now we can see that if we were to make a guess, all right, let's just do one more, C5, we could just probably guess that that's going to be 5 2s, all right, so notice 4, there's 4 of them, 3 2s, etc. So we're trying to guess a pattern as to what's going on with this. So it's going to be 2 times 2 times 2 times 2 times 2, C0 divided by 5 times 4 times 3 times 2. All right. Now, if I was to make a guess, and that's ultimately what we want to do with this, is we need to make a guess, I'm going to guess the nth iteration. So C sub n is going to be equal to 2 to the nth power, right? Because each time this is 2 to the 5th, right? And that means the index is 5, so that's 2 to the 5th, 2 to the 4th, c sub naught, and then in the denominator, notice we have 5 times 4 times 3 times 2. Implicitly, there's a 1 there, right, because we can multiply anything by 1. And isn't that the definition of 5 factorial? And so wouldn't that mean that the denominator becomes n factorial? And that's what we're looking for. We're looking for some sort of generating function, and we're trying to figure out, okay, well, what eventually is going to happen? What's the long-term behavior of c sub n? Now remember our original power series, right? Way back, we said y was equal to series n equals 0 to infinity, c sub n x to the n. But didn't we just solve for c sub n? So we could plug that back in, and now y is going to be equal to the series n equals 0 to infinity, 2 to the n c sub naught over n factorial times x to the n. Another way to write this is to factor the c naught out. So let's just factor the c naught out because that's just a constant. Series n equals 0 to infinity. And that's going to be, notice we have a 2 to the n and an x to the n, so we can write that as 2x to the n over n factorial. All right, so that's our solution, our series solution. What does that mean, if anything at all? Well, remember those power series that we talked about earlier, right? And by the way, I will show you how to get the initial value for this, but remember all the way back up, we had this table, these common power series, right? And hopefully, this one looks pretty familiar, doesn't it? Because that's what we just figured out, except we have a c naught and we have an x to the 2n. So I would just replace x with 2x, and so really we could just rewrite this as c sub naught e to the 2x, right? Because this is the power series representation of e to the 2x, because it's not x to the n, it's 2x to the nth power. All right, and so check this out. Remember a long time ago, like almost 15 minutes ago, remember this solution that we got? We got y equals k e to the 2x. We have c sub naught e to the 2x. Right? So that's pretty cool that now we just found a power series solution, and obviously it took a lot longer to do it than separation of variables, and it did require more extensive knowledge, but we were able to do it very nicely. Now I'm going to stop the video here, and I'm going to make a shorter video to show you how to take care of the initial value for the series. But maybe go back through and look at the techniques again before going on to the next problem.